This talk is about curves and equations and how each of these can represent the other. We'll ask, who introduced Cartesian coordinates and which equations describe lines and conics? And we'll also see some historic curves and their equations. Diagrams have long been used to illustrate numerical information, such as an Egyptian tablet from about 2600 BC depicting the height of an arch at points along its length. In the 14th century AD, the French mathematician and philosopher Nicole Oraim wrote a treatise showing how to represent graphically various qualities, such as the speed of a moving object, using a horizontal axis, the longitude, for points along the journey, and a vertical axis, the latitude, for the speed at each point. Below are two of his diagrams which illustrate uniform behaviour, such as constant speed, and accelerated motion, but without calculating the latitude at any specific point. The main advances in graphical representation had to wait until the 17th century with the development of so-called analytic geometry. Increasingly, algebra began to be used to investigate problems from geometry, linking the presentation of data with the mathematical equations describing them, and using the new algebraic notation then being developed. Involved with these advances were the French lawyer and mathematician Pierre de Fermat and the philosopher René Descartes. Both were interested in locus problems, where we seek the path of a point in the plane moving under specific conditions. For example, the locus of a point which is always at distance 1 from a given point O is the circle of radius 1 with O as its centre. And the locus of a point that's equidistant from two intersecting lines is the line that lies halfway between them. A much more complicated problem, solved by Descartes, was first posed by Pappus of Alexandria in the 4th century AD. Here we're given 4 fixed lines, 4 angles, and a number k, and we seek the path traced by a point P that moves in such a way that its distances d1, d2, d3 and d4 from the 4 lines satisfy the equation d1 times d2 equals k times d3 times d4, where these distances are measured along lines from P that meet the 4 lines in the given angles. The relevant picture is shown above on the right, but don't worry about the details. The important thing is that to solve this problem, as pictured below, Descartes wrote x for the length of one line and y for the length of another line. He then calculated the distances in terms of x and y and showed that the equation d1 d2 equals k times d3 d4 is a quadratic equation involving such terms as x squared, y squared and xy. And this means, as we'll see later, that the required path is a conic such as an ellipse. So Descartes used algebra to solve a problem in geometry. But the x and y he introduced there are not the same x and y as those we usually use when drawing graphs, even though they're named after him as Cartesian coordinates. For us, as shown on the left, the x-axis is a pre-assigned horizontal line. The y-axis is a vertical line crossing it at a point called the origin. And a point xy is then x units to the right of and y units above the origin. Here you can see the origin 0, 0 and the points 2, 3 and -3, 1. It's not known who first introduced these coordinates. It may have been Fermat, although his axes weren't always fixed in advance and weren't always at right angles. But axes at right angles gradually came into regular use, as depicted on the right, in a graph produced by the astronomer Edmund Halley in 1686 to depict atmospheric pressure. We'll now look at lines and conics and their equations. Straight line graphs correspond to linear equations, equations involving x and y, but no higher powers such as squares or cubes. On the left, you can see the diagonal line with equation y equals x, where the x and y coordinates are equal at every point. Also here are the vertical line with equation x equals 2 and the horizontal line with equation y equals 1. On the right are two forms of the equation of a straight line. Above is y equals mx plus c, or in some countries y equals mx plus b. Here, m is the slope of the line as shown by the little triangle. It's the ratio of m over 1. And c is the intercept, the point where the line meets the y-axis. The second form is x over r plus y over s equals 1, shown below, where r and s mark the intercepts on the x-axis and y-axis. Either of these equations can also be written in the form ax plus by equals c, where a, b and c are all constants. These are all called linear equations because they're the equation of a line. We next move up a step to quadratic equations and to the curves called conics, which are caused by slicing a cone, or rather a double cone, in various ways. Slicing it horizontally gives us a circle, while slicing it at a skew angle gives an ellipse. Slicing it vertically gives a two-part curve called a hyperbola, while slicing it at an angle parallel to the side of the cone gives a parabola. We'll now look at these in turn, together with their equations. To find the equation of the circle on the left, with its centre at the origin and with radius r, we see from the right-angled triangle with longest side r that, by the Pythagorean theorem, the point with coordinates x and y satisfies the equation x squared plus y squared equals r squared. For a circle with its centre at the point AB but still with radius r, the corresponding equation is x minus a all squared plus y minus b all squared equals r squared. For the parabola, it's been known since Greek times that this is the locus of a point whose distance from a fixed point, called the focus, is always equal to the distance from a fixed line, called the directrix. Here, the focus is the point F, with coordinates a, 0. And the directrix is the vertical line x equals minus a, passing through a point D. And so for any point P on the parabola, the distance from P to F is equal to the distance from P to D. If P is the point xy, we can then calculate these distances. Don't worry about the details. And we get the equation x minus a all squared plus y squared equals x plus a all squared, which simplifies to y squared equals 4ax. For ellipses and hyperbolas, the situation is similar, except that instead of the distances from P to the focus point and to the directrix line being equal, the distance to the focus is now always a constant multiple e times the distance to the directrix line, where e, the eccentricity, is less than 1 for the ellipse and e is greater than 1 for for the hyperbola. For both curves, the focus is then the point AE 0, and the directrix is the line x equals a over e. If we now calculate the distances from P as before, and again don't worry about the details, we find that the equation of the ellipse can be written as x squared over a squared plus y squared over b squared equals 1, and that the equation of the hyperbola can be written as x squared over a squared minus y squared over b squared equals 1, which is similar except for the minus sign. For a hyperbola, the dotted lines that the curves approach but never reach are called asymptotes. Two further comments. Another way to draw an ellipse is to tie a rope to two pegs and then trace out the curve. This method has sometimes been used by architects and surveyors, and also by gardeners when designing elliptical flower beds. And for the hyperbola, if its asymptotes are at right angles, then as pictured below, we can rotate them to get the much simpler equation y equals k over x, or xy equals k, where k is a squared over 2. Many important curves have equations of the form y equals a polynomial in x. Polynomials are obtained by adding multiples of powers of x. For example, as we've seen, straight lines correspond to linear equations of the form y equals mx plus c. For quadratic equations, those with an x squared term, the equation y equals ax squared plus bx plus c represents a parabola, which is cup-shaped if a is positive, and the other way up if a is negative. For cubic curves with an x cubed term, the equation y equals ax cubed plus bx squared plus cx plus d looks something like this. When a is positive, the right-hand end increases indefinitely as x increases, while the left-hand end decreases indefinitely. And if a is negative, it's the other way around. But there are other types of cubic curve. Just as quadratic curves basically come in three types: ellipses, hyperbolas, and parabolas, and with equations involving terms in x squared, xy, and y squared. So cubic curves come in different types with terms in x cubed, x squared y, y cubed, and so on. And in fact, as Isaac Newton found, in work that was far ahead of its time, there are no fewer than 76 types of cubic curve. And he found all 76, publishing most of them in a book on optics, which he wrote in 1704. Here's one of them. Over the millennia, many types of curve have arisen, often through attempts to solve particular problems, mathematical and otherwise. Here's one from Greek times. It's the conchoid of Nicomedes, meaning like a conch shell, which arose when he was seeking a general construction for dividing angles into three equal parts. Given a fixed horizontal line L at a height of a above the x-axis, we draw dotted lines from the origin O to point C on this line. And then we extend each dotted line by a fixed length k to new points labelled C'. These points C' then trace out the conchoid. Its equation is shown below. Here are some more curves that have arisen through history, together with their equations. Above is a cardioid, or heart-shaped curve. The figure of 8 curve known as a lemniscate, which was actively studied in the 17th century, and a four-leafed rose. Below are two curves named after their discoverers. The folium of Descartes, which he studied in the 1630s, and here the dotted line is an asymptote, and the so-called Witch of Agnesi, named after the Italian mathematician and textbook writer Maria Agnesi. She was not a witch, the word was a mistranslation of sailing sheet. We conclude with a brief visit to higher dimensions. On moving from 2 to 3 dimensions, there are now 3 axes in the x, y and z directions. The points now have 3 coordinates, such as 0, 0, 0 for the origin, and A, B, C for a general point. Planes then have equations of the form ax plus by plus cz is a constant, while a line, being the intersection of 2 planes, now has 2 equations. For example, the line with the equations here is the intersection of the 2 planes with equations x minus 2y equals 0 and x minus 3z equals 0. We can even move to yet higher dimensions. For example, in 4 dimensions, a general point now has coordinates a, b, c, d, and similarly for dimensions 5, 6 and higher. Mathematically, these are no more abstract than the plane or 3-dimensional space. The only difference is that we can no longer visualize them. And with that intriguing thought, I thank you for listening.